students, today we are going to see another experiment in physics in the section heat. This is about determining the specific heat capacity of water using the electric method. So, here some knowledge from electricity is also required, right. I will explain you whatever the required knowledge from electricity as well, but actually if you have studied electricity already, then this experiment will make more, it will be easy to understand, right. See what we are going to do here. Can you see this is a calorimeter, right. We have filled it with water. And inside that we have kept a heating coil. Can you see a small coil is there? And the coil has been connected here. The two ends of the coil are connected here. And we have given we have completed the electric circuit here. Can you see? This is one side of the battery. There is an ammeter. You know, ammeter and voltmeter. Ammeter measures the current, how much of current flows through the circuit. Voltmeter measures how much of voltage is dropped within a particular part of this circuit. Ammeter has to be connected in series in the circuit. Voltmeter has to be connected in parallel to the equipment where you want to measure the voltage drop. You must know that. So, ammeter has been connected here in series with the circuit. And this is a variable resistance. We have something called rheostat. Why we take variable resistance? See, if we have a circuit with two resistance, right, R1, R2. The voltage, say if this is V, the battery is with V voltage, how much of this V will fall into R1, how much of this V will fall into R2 is decided by the ratio between R1 and R2. See, for example, if you have V1 voltage drop in this, V2 voltage drop here, we can say V1 to V2 will be R1 to R2. This is some knowledge from electricity. So, now in this circuit, if you see which are the resistant parts mainly here, one is this heating coil, other one is this resistance. These two are in series. Can you see? Look at the circuit. These two are in series. Let's say this battery or the power supply is of 10 voltage, but I need to get only 5 voltage here. So, half of it is required there, right? Then we can adjust this rheostat such that I get 5 voltage here. Or let's say you don't want 5 voltage, you want 4 voltage. Again adjust this, increase this resistance so that the proportion of the resistance of the coil decreases and the voltage drop within the coil decreases, right. So, because of that we are using a rheostat here, a variable resistance. Rheostat means the variable resistance. I can adjust it and I can change it to different resistant values within the range. It will have a range, each rheostat will have a range. So, within that range from 0 to that range, suppose let us say this is 10 ohm rheostat. So, 0 to 10 ohm I can adjust it, clear. And then we have a switch. We have a special type of switch that we use in electricity experiments known as plug key. Plug key, it works like this, right. There will be a gadget where plus and minus will be connected. In between there is a key. So, once you unplug this key, once you remove this key, circuit is not closed, circuit is open. So, the current flow, the electricity flow will not happen. Once you insert this key, right, once you plug this key in, then the circuit is closed and electricity will flow, the current flow will happen. We call it a plug key. When I do the experiment, I will show it to you. That is the kind of switch we use here, right, to improve the precision, because when you are removing it, At the same time, I may have to switch on the stopwatch as well to measure the time. And there shouldn't be any time delays. There shouldn't be any sparks that happens. So this kind of switch is preferred in electricity experiments. So what actually happens here, you know, at home we sometimes use a heating coil to heat water. Even if you take an electric kettle, what is there within electric kettle? There is a heating coil. Sometimes they might have closed it with a plate, but actually it's a heating coil there. So when the electricity flows through that coil, the electric energy is converted into heat. It consumes electricity and it releases heat. So there is a transformation of electric energy into heat, right? The electric energy that is consumed by the particular coil for within t seconds can be written as IVT. IVT is the I is the current, V is the voltage, T is the time it has been on. IVT is the electric energy it has consumed. And that IVT, the coil converts into heat. So basically the heat emitted by the coil should be equal to IVT. And if there is no heat loss to the environment, see, when we do it at home, there is heat loss. Because when you use the kettle, right, the kettle surface gets heated. So it loses heat to the environment. But here we don't do that. Here, can you see, we have kept a vacuum in between, right, and we have closed it. We have closed it. Why did we close it? So that the convection doesn't happen. Why do we have a vacuum, or sometimes we may use a different liquid or something? Why do we use that here? To reduce the heat loss to the environment by means of conduction. Heat can be lost through three formats: heat conduction, heat convection, heat radiation. So to prevent heat loss to the environment by the means of convection, you close it. Close it. To prevent the heat loss by conduction, you lag it or insulate it. Lagging or proper lagging will be done here. And to prevent the heat loss by radiation, you keep the outer surface polished. A shiny surface will reduce radiation. Right, so we will take all those precautionary measures to ensure the heat loss to the environment is minimized. Right. Then what do we do? See, we connect the circuit. Why? The moment you connect this circuit, the moment you close the circuit, switch on the stopwatch also. You can measure, see, we have a thermometer here. We can measure the initial temperature of water. Let's say temperature initially it's 30. You wait for some time until it comes to approximately 5 degree or 10 degree. Then, you know, IVT is the heat that has been produced by this coil. That has to be equal to MC delta theta. Of whom, MC delta theta of whom, who are gaining that heat released by this coil? One, the water. Two, this calorimeter and this stirrer, they also gain the heat. When you finish the experiment, let's say at 40 degree, the calorimeter is also going to be at 40, which was not at 40 when we started, which was at 30. So calorimeter going from 30 to 40 means calorimeter also gains a heat that has been released by this coil. So MC delta theta for water, MC delta theta for calorimeter and stirrer together. All put together should be equal to IVT. One more adjustment we can do, still like there can be, even though you have done proper lagging and all, still there can be some heat loss to the environment. So we do this cooling correction. What is that cooling correction? Suppose if the environmental temperature is 30, you start the experiment at 25 and finish the experiment at 35. So from 25 to 30, the temperature of the system is less than the environmental temperature. So it gains heat from the environment. 30 to 35, the system temperature is bigger than the environmental temperature. So it loses heat to the environment. Clear? So we can do that kind of cooling correction as well, so that the heat gained from the environment, heat lost to the environment can be assumed to be approximately equal, right? So that adjustment is also possible. Finally, what calculation we are going to do? IVT equals I is measured by ammeter, V is measured by voltmeter, T is measured by the stopwatch. M is going to be measured by 3-beam balance, or you can say chemical balance. C is what we have to find for water. Calorimeter C is usually the specific heat capacity of copper. We assume it to be 420. Delta theta, the thermometer will help us. You measure the initial temperature, end temperature, get the difference, that will be the delta theta. Apply the formula IVT equals MC delta theta of water plus MC delta theta of calorimeter. Apply the formula, only C of water is the unknown, you can find it. Clear? This is the very simple experiment we are going to do, right? And you need to understand, at home when we are doing this, like when you are heating water, what we connect is 230 voltage supply. Whereas what we are going to do here might be around 4 voltage, 5 voltage supply. So the time it takes to heat this water would be much higher, can be even like half an hour, 45 minutes. If you want to minimize that, take this calorimeter in a small one, so that the amount of water is less, so that you can finish the experiment faster. Why do we have to finish the experiment faster? So that this environmental, the heat transfer to and from environment can be minimized, right? When you take longer and longer, heat transfer with the environment is high. So if you want to finish the experiment faster, we have to take small amount of water. Doesn't mean in a big calorimeter, if you keep little amount of water, that will be an error. You have to make sure this coil is fully submerged here, right? So take a small calorimeter and fill it with water. Okay. So that's the concept of this experiment. Let's see what further steps we have to do. Look at the concept again. When voltage V and current I are supplied for time t, then the amount of electrical energy consumed is given by Q equals IVT. This electrical energy is converted into heat. That's what the coil does. If there has been no heat lost to the environment, the electrical energy consumed will be equal to the heat gained by water, calorimeter and stirrer. IVT equals MC for calorimeter, MC for water and delta theta. Clear? Materials and apparatus. A calorimeter with polished outer surface, lid and a stirrer. All that is required. Thermometer, small heating coil, voltmeter, ammeter, battery, rheostat, stopwatch and a plug key. Plug key, I explained what it is. A switch basically, it's a switch, electric switch. Method. Measure the mass of empty calorimeter and stirrer. Fill it with water for approximately 2/3 of it and measure the mass again. Connect the battery, plug key, ammeter, heating coil and the rheostat in series and connect the voltmeter in parallel to the coil. I explained you. Ammeter is usually connected in series, voltmeter is connected in parallel. Keep the coil in another beaker with water. Close the plug key and set the rheostat until the voltmeter shows a stable reading about 4 volt. What is the meaning of keep it in another beaker? See, when you do these calibrations, when you do this tuning, don't keep the coil in this same calorimeter. Because when you are doing the tuning itself, there might be changes in temperature, right? So better thing, keep it in a different beaker with water. If you just keep it open to the environment, sometimes because of overheating, the coil can be burnt. So don't keep it in the open space, submerge it in another beaker with water, right? Tune your voltmeter, adjust your rheostat and get the required amount of voltage, required amount of current. Make sure voltmeter and ammeter show you stable reading. Once you got that, now remove the plug key. That means you open the circuit, current doesn't flow. Take it, bring it to the calorimeter where you are actually doing the experiment. Now again close the plug key, switch on the stopwatch and do the experiment, right. So when we do the calibration, when we do the tuning, we keep the coil in another beaker with water and do this. Open the plug key, take the coil from the beaker and submerge it within the calorimeter with the water. Record the initial temperature of water, theta 1. Simultaneously close the plug key and start the stopwatch. Simultaneously, when you are closing the plug key, at the same time you have to start the stopwatch also. Record the recordings of ammeter and voltmeter. After the temperature of water has raised about by 10 degrees centigrade, stop the stopwatch and open the plug key. Record the stopwatch reading, and that's the time, how long you have been doing this experiment, and the final maximum temperature of water. Like you have to keep stirring it throughout the experiment. You have to keep stirring it and measure the final temperature. Clear? Then the calculation you are going to do is IVT equals, we already saw that, IVT equals calorimeter stirrer, water, delta T. Delta T means theta 2 minus theta 1. We know I, we know V, we know T, we know MC, CC, MW, theta 2, theta 1 we know. Only CW we don't know. We can calculate it. Clear? So that's the concept. Quite easy, straightforward steps. Let's do this experiment and see how it works. You can see now this is the calorimeter in which we are going to have the water and we are going to heat it. The lid of the calorimeter is a special one. You can see there is a coil here. See, there is a small coil, right? There is a small coil here. So how it works is, in these two ends we will be giving the electricity supply, plus minus, you can give it to either side of it. So the electricity will flow through this. So this is the coil that is going to heat. And then we have a stirrer fixed here, a stirrer. That is the calorimeter. And to thermally insulate the calorimeter, we will be using this sponge, right. We will wrap this calorimeter with this sponge, right. Also, we will be using a voltmeter to measure the voltage drop within this heating coil, and an ammeter to measure the current that runs through or that flows through the heater. This is the voltage supply. This is the voltage supply which we can connect to the main supply, and we can get 5 voltage, 6 voltage, that kind of voltage we can, direct current supply we can get from this. It converts the AC supply in the main, AC voltage in the main supply to direct voltage, direct current voltage, to a reduced level like 5 voltage, 6 voltage, that level we can get it. And this is the rheostat. I will explain how to use this. This is basically a resistance that we can change, right? A resistance which we can change the amount of it and we can use it, change the value of it and we can use it. I will show you how to use this as well. And this is what we call plug switch, basically a switch. Plug switch, we will be using this in the circuit. When I am connecting in the circuit, I will explain how it functions. To complete the circuit, we need pieces of wire. These are the wire pieces we will be using. Yes. And stopwatch to measure the time, how long we are giving the supply, stopwatch. A beaker with water. This is the water we are going to fill in this calorimeter and heat it up. To measure the temperature, you need thermometer. And as I mentioned earlier, we have to measure the weight of calorimeter, stirrer, and then the water. For that we need a 3-beam balance, right. These are the apparatus that we are going to use in this experiment, right. One by one, when I am connecting the circuit, I will explain how we are going to use each of them, right. Maybe since you have not done the electricity part yet, some of you might not be familiar with these rheostat and all. I will show you how we can use them in the circuit, right. So, shall we see how we are going to connect it to the circuit? Before connecting the circuit and we start the experiment, let us measure the mass of calorimeter with stirrer. See, I have taken the stirrer separately. So, only the calorimeter and stirrer are here. Let's measure the mass of them. It's less than 100. More than 20, 40, 60, 70, it's less than 80, it comes 77.4 grams. 77.4 grams. That's the mass of calorimeter and the stirrer. Now what we will do, let's fill this with water, right? Let's fill this with water and measure the mass again. So you need to have sufficient water to submerge the heater, the heating coil fully. Right, with that much of water, let me measure the mass of it again. Let's bring back everything to 0. Hundred, 200, 300. It's less than 400. So let's keep it at 300. It's more than 370. We get 372.4 grams. 372.4 grams. That is MC plus MW. Let's mark these down. Let's write these down in a table before we connect the circuit and start doing the experiment. MC, we got 77.4 grams. Let's write it down. 77.4 grams. And MC plus MW, we got 372.4 grams. 372.4 grams. 372.4 grams. Now what do we do? Let's make the circuit. Let's send the current or electricity through the heating coil. Measure I, the current in amperes. Measure the voltage drop within the heater in volts. Right? Measure the initial temperature of the water. Approximately 10 degrees, let it go up and take the time, measure the time it takes for that T, right? Then we can fill all these. As I explained earlier, then we can do IVT equals MC delta theta of water, MC delta theta of calorimeter plus the stirrer, right? We can equate that and find the C, the specific heat capacity of water. Let's see how we are going to connect the circuit now. Students, as I mentioned earlier, I have arranged the calorimeter with the thermometer inside. Already I filled it with water and now thermometer is in, the heating coil is in, stirrer is in. Also I have wrapped it with the sponge to do a proper lagging so that there is no heat loss by conduction from this calorimeter. Also, it is kept on top of a, you can see a Regifoam piece, so that there is no heat loss to the environment by conduction. At the same time, since we have a lid, there won't be any convection happening from this calorimeter. And the calorimeter is with a shiny surface, so that radiation also will be prevented. So, we have taken all the measures to prevent heat loss from the calorimeter to the environment. Right? Okay. Now we are going to connect this. This is the DC supply. Once we connect it to the main supply and switch it on, we will get the DC supply from this. So how we are going to connect the circuit, I am going to show it to you now. See, This is the switch I told you. Let's try to understand how this switch works, right? See, I'll connect one wire, one piece of wire to one end of the switch, and this will be given to the power supply. This will be given to the power supply, right? And then from the other end, I will connect it to the circuit. So, what happens here? See, we have a small key here, we call it plug key. If we insert here, the circuit will be completed. So, again you can see it clearly. See, this is how the electricity flow is going to be. The electricity that comes through this cable or this wire goes through this way. See, if I remove this key, we call it the plug key. If I remove this key, then the circuit is not complete, it is incomplete. Right? So, the current supply, electricity supply will be disconnected. When you insert it in here, the circuit will be completed. That is the function of this switch. We call it a plug switch, right? A plug key switch or plug key, right? Usually they call it plug key, you can call it plug switch as well. So, that is the plug key. Then, let me take it and connect it to the rheostat. Let me show you how the rheostat functions. Let us try to understand the functionality of rheostat. Look at this carefully. See, this is the rheostat we call it. What happens here? Let us say I give the connection to this end. Right, you can see there are 2 points where we can connect the wire. So, let us see I have connected here and connected another piece of wire here. Try to understand this. So, what happens now? The electricity comes through this wire, will go through all these, this is the resistance here. This is the resistance. So, it goes through the entire resistance and it will come out from here. So, if you have connected like this, however you change this top part, you can see this top part, there is a clamp. However you change this or however you shift this clamp, there is nothing happening because the electricity that comes through this end, actually this is like a wire coil. So, it has to go through all those coils, all those wire, and it will come from this end. Then it is not functioning like a rheostat. Right? It is functioning like a fixed resistance. If you connect between these two, this is functioning as a fixed resistance. This is functionless if you have connected between these two. So, how do we use it as a variable resistance? You should not connect between these two. Here, if you have connected like this, on the other end, you can connect it here. Now, I will show you how the electricity flow happens. See, the electricity that comes through this wire comes here in up to see. You can see here. Can you see the clamp part here? See the electricity that comes from here. Can you see? There is this clamp. Can you see there is a clamp? So, from here it enters into the resistance. It goes through all these coils, it comes here. At this point, it enters into this part, and from here it comes through this rod and it comes out. Look at the path again. The electricity that flows from here, from this point to this point, it goes through all this coil, and then it comes here, goes through this rod, and it comes out. So, see, out of the total resistance, you have used only this part of resistance, right? Basically, this rod is assumed to be a negligible resistance. It does not have any resistance, so it is negligible. So, the resistance that is going to be used here is only from here to here. Only from here to here. Out of the full resistance, you are using only this much. Suppose you want more resistance here, push it here. Then you are using this much of resistance. Suppose you want to use less resistance, push it towards this point. Understand? So, this is how you connect the wire in this rheostat. Equally, you can connect like this also. Look at this. if you connect it here, still it is a variable resistance. Why? Look at this. The current that flows from here, then it goes through this part. See, it goes through all this part, again enters here, comes to the rod and it goes all the way. So when you connect it here, the resistance that you are going to use is in between these two. This is the value of resistance that you are going to use. When you connect it here, the resistance you are using is here. Careful, there have been questions about this, how you connect the rheostat, when it is connected like this, what is the part of resistance you are using, all those questions have been tested. So understand how the rheostat is going to be used. So if I connect it here, okay, I'm going to connect it here. In this experiment, I'm connecting it here, and then I'm connecting it this way. Right? There had been questions, a student connected like this, and when he changes this, he doesn't see any change in the volt or ampere. Why is that? Because he is not using this as a variable resistance. When he connect between these two, he is actually utilizing the full resistance. This doesn't work. This will work only if the electricity flows through this part. So how do you make the electricity flow through this part? Connect at least one wire to this end. Then the electricity that enters from either this pin or this pin, okay, if it enters from this pin, it flows all the way here, enters here and goes out. You understand? So this is how we fix the rheostat. Okay, I have fixed the rheostat also. Right? Still I have not given the power supply. You can see that, right? This side is open. I have not fixed the power supply. Right? After I complete the circuit, I will fix the power supply. Okay? Right. Then after it comes from the rheostat, let me connect it to the calorimeter with the heating coil. Let me connect it here. So from this end, the electricity goes in. You can see that. See, it comes all the way from here, rheostat, and then it comes here. From this end, the electricity goes in. It goes through the heater, and let me take it out from the other end. Right. Now, the heating coil within the calorimeter is connected. What do we connect after that? We have a voltmeter and ampere meter, ammeter. This is the ammeter, right? You can see this is the ammeter and this is the voltmeter. So you know ammeter has to be connected in series. Voltmeter has to be connected in parallel. So finally I will connect the voltmeter in parallel to this heating coil. Now ammeter has to be connected in series. Let's connect the ammeter. Right? See, I am connecting it in series. Again, see the power. I will keep the voltmeter away. We will connect it at the end. You can see the supply that is going to come from here comes through the switch, the plug key basically, rheostat, and it goes to the heating coil. It comes out from the heating coil, goes to the ammeter. From the ammeter, let me take it out. Right, it comes from this way. Now I can connect this back to the power supply. So this, if this is the positive side of power supply, this is going to be the negative side of power supply. Right? So let's give it to the power supply. See, I have not switched this on yet. Let me connect it. To be on the safe side, let's remove the plug key so that circuit is not yet functioning. Right, let me connect it here. Right. So now the circuit is complete. The moment I fix the plug key and I switch it on, the current will flow, the electricity flow will happen. I have to connect the voltmeter, don't forget that. Let me connect the voltmeter also. See, voltmeter, as I mentioned earlier, it has to be connected in parallel. So from here we will take two wires away and connect it to the voltmeter. Look at this carefully. Voltmeter, I have to give a parallel connection. parallel connection. Right, here let's connect the voltmeter. See, it's a parallel connection. It is not in series, it's just a parallel connection. Parallel to the heating coil, I am connecting the voltmeter. All right. Now my circuit is complete. So what I am going to do? First, I am going to adjust it to approximately 4 volt of electricity supply. So when I am doing this calibration, I should not keep this heating coil inside this water. Do you know why? After I do all the setting only, I should come and submerge it in this water. While keeping this in this water itself, if I do the calibrations, if the electricity flows through this, then during the calibration also there will be some heating of water that will happen, which will not be captured in your IVT. So first what I will do, I will take another beaker with water. In that beaker I will keep this and I will calibrate it to approximately 4 voltage, a stable voltage and stable current. Once I have got a stable voltage and stable current, then I will switch it off, bring it here and fix it here. Right? So shall we see how we are going to do the calibration of it? Students, you can see I have connected everything now as I shown you earlier. I have not completed the connection. The plug key has been removed, you can see. So there is no electricity flow, Now what I am going to do, I have to get approximately 4 voltage, right? So what we will do, as I mentioned earlier, we will take it out from this calorimeter. You can see I have another beaker with water. Let's submerge it there. If you don't have water, if you just keep it on the air, sometimes the coil might get overheated, right? So to avoid that, just keep it in a beaker of water. And now I have already connected to this, right? The DC supply, it has been connected here, right? Let me switch it on, right? DC supply switch on. Now I am getting the DC supply from here. Still the current doesn't flow, still the electricity flow doesn't happen because the plug key has been removed. Now let me connect this and see. See what happens, right? You can see both the voltmeter and ammeter, they show some readings, right? Look at the readings, what they show now. Ammeter is approximately 1.2 voltage approximately. 1.4, approximately 1.4 voltage it shows, and the ammeter it shows around 0.4 amperes, right? 0.4 amperes. But I want to get approximately 4 voltage. That's why I am going to use this rheostat. You can see that. See, now as per my connection now, the electricity flows from here and it goes all the way here and it enters or it exits from here. So this is the amount of, you can see, this is the amount of resistance that is being used. Since I want more voltage to fall into the heating coil, let me reduce the resistance here, right? You know, 2 resistance in parallel. In proportion to the resistance, voltage will drop. So if you want to increase the voltage drop here, reduce the other resistance. Let's reduce it. See what has happened now. Still the same. Let's reduce it further. See, when I am reducing it, you can see here the voltage drop increases in this heating coil. Let me reduce it further. Can you see it has gone up to 2, right? Can you see it has gone close to 1.9? Yes. Let me reduce it further. Can you see it keeps on increasing? So basically I am reducing the voltage, reducing the resistance here. So that proportionally, the proportion of the resistance of the heating coil increases. When the ratio increases, more voltage drops there. Let me reduce it further. I like to get close to 4 voltage, not exactly 4 it has to be. Let's try to get somewhere close to 4. Maybe I can increase a little bit further. It's 4.5. Maybe I can reduce it a little bit. Right. Can you see how much it is now? See, there is one thing you have to understand. Usually we keep this voltmeter and ammeter to the person who is doing experiment to his side. So basically I have to keep it to my side. Here, why I have kept it like this is to show you clearly. Right, when you are doing the experiment, don't connect it like this, turn it to your way so that you can see that you can observe it easily. So this is, I have kept it so that you can watch it comfortably. Right, you can see now we have got 4 voltage here. See, 4 voltage. And what is the current? It is at 1.5 amperes. 1.5 amperes. Let's just observe it, see whether it is stable. If it is not stable, then you have to wait until it's stable. Yes, I'm having a stable voltage and stable ammeter reading. Right, now I have calibrated everything. Let me remove the plug key now. Right. So see, after you have started the experiment, you don't have to switch this off. That gives you the supply. You have a switch here, the plug key. So remove it, it's disconnected. Insert it, it's connected. Right. Now what shall we do? Let's take it again. Let's take it again and fix it here. Before I start the experiment, right, before I complete the circuit now, I need to measure the initial temperature of water. Yeah. So let me check the initial temperature of water. It is it is at 23 degrees. It is at 23 degrees, right? I have taken water which is a little bit, which is at a temperature lower than the environmental temperature. The usual cooling adjustment we have done, cooling correction. What is it? If the environmental temperature is around 28, 29 degree, we usually take a, if you want 10 degree increment, take 5 degree less from the environmental temperature, and then you end the experiment 5 degree above the environmental temperature, so that heat gained from the environment and heat lost to the environment will be approximately equal. Because of that, I have done that adjustment. So initial temperature is theta1, which is 23 degrees. Now what am I going to do? I have the stopwatch here, right? The moment I connect this, I have to start the stopwatch also, right? And time to time I have to keep stirring it. Time to time I have to keep stirring it until if I want 10 degree extra, approximately to 33 degrees, I have to wait until it comes to 33 degree. One more thing you need to understand, unlike the heating coil you use at home, this is a very small one. So to heat, even though it's a small amount of water, it might take more time, 20-25 minutes it might take, right? So you have to wait for so much time and measure the temperature increment. So usually we study, if we do the experiment for a longer time, that will have errors because the heat transferred to the environment will be high. If you want to reduce that, couple of options for you, take less amount of water. Maybe you can take a smaller calorimeter, take less amount of water. Or you can use a bigger coil so that the voltage drop is more here. Or you can even reduce the rheostat, the resistance here, and give more voltage. But usually around 4 voltage, 4 ampere within this level is what is suggested to do experiments within the laboratory, right? So better idea might be, if you want to reduce the time it takes, you can reduce the amount of water. Maybe a smaller calorimeter would be another idea, right? So now I'm going to insert the plug key. At the same time, I'm going to switch on my stopwatch as well, right? So let me switch it on now, having the stopwatch ready. Right. Let's check the ammeter and voltmeter readings again. Voltmeter is at 4 voltage, you can see that it's at 4 voltage, and ammeter reading is at 1.5 amperes. It's stable 1.5 amperes, right. So, V is 4 and I is 1.5. Now, let me keep stirring it time to time and checking the temperature, right. You can't expect the temperature to rise rapidly, it will take some time because as I mentioned, it's a very small coil and very small voltage that we are supplying there. It will take time. Let's time to time keep stirring it and measure the temperature. I started at 23. Students, now the temperature has gone up to 28 degrees. It has gone up to 28 now. We started at 23, now it is 28. Let's keep stirring it until it comes to 33 degrees. Yeah. Now you can see it is just passing 30 degrees. It has come to 30 degree now, 30. Let's wait until 33. As I told you, it is going to take much more time because the coil is very small, voltage drop is very small, I is very small, so it's going to take a lot of time. I and V are two small values that we are using here in this experiment. So patiently you have to keep doing it. Students, you can see it has come to 32 here, 32. Right, let's keep stirring it further. Students, you can see now it has come to 33 degrees. Let me switch off, let me stop the stopwatch now and remove the plug key. And the reading I have got in the stopwatch is 36 minutes and 10 seconds. 36 minutes and 10 seconds I have got. Right, this is what I told you, since this the coil is too small and the voltage and the ampere we are using is very small, the time takes can be very high. It has taken 36 minutes and 10 seconds. Right, let's write down all these readings on our table now. Right, voltage 4, ampere 1.5, the time taken 36 minutes and 10 seconds, right, and the theta 1 was 23 degree, theta 2, the end temperature of water and calorimeter is 33 degrees. Shall we write down all this? I 1.5 amperes, voltage 4 voltage, time it took 36 minutes and 10 seconds, 36 minutes and 10 seconds. Theta 1, the initial temperature 23 and the final temperature was 33 degrees. As I mentioned earlier, now we can say the electricity consumed, which is IVT, electric energy consumed, IVT should be equal to MC delta theta of water and calorimeter with stir. Let's do that calculation where we know I, V, T, we know delta theta, we know the M of both calorimeter and water. We usually know the specific heat capacity of the calorimeter, right, which is copper. We usually take it as 420. So, only thing that we don't know is the specific heat capacity of water, which theoretically we studied as 4200. Let's do the calculation and see whether we get a value close to that. Students, you can see the readings I have got. I have put it into a table here, MC, MC plus MW. So, if you get the difference here, that will be MW, isn't it? That will be 295. I, V, time is in minutes and seconds. Let's convert that to seconds. First multiply by 60, 36, 3, 21, and there is another 10 seconds. So, that is 2170 seconds. Theta 1, theta 2 is there. Good. Now, let's do the calculation. IVT equals MCCC plus MWCW delta theta. Delta theta means theta 2 minus theta 1. Theta 2 minus theta 1. I 1.5 amperes. For how much was T? 2170. MC we have got 77.4. Convert that to kilograms. Cc, copper, the calorimeter is made of copper. Copper C, the specific heat capacity of copper is assumed to be 420. MW 295. CW we don't know. Theta 2 minus theta 1 is 10. Let's solve this. How are we going to solve this? The 0 and 0 can be cancelled. This will be, this is 6, 6 into this is 42, 6 plus 4, 10, 13, and this 1000 comes up equals 77,442. Let's multiply and see that. 774,42. 8, 4, 15. 3096. 8, 10, 5, 2, 3. 32,508 plus 295 CW. Subtract it here, you get 492, 127, 295 CW. To find CW, we are divide by 295 now. $295. 4, 22, 36, 38, 3, 11, 91, 4, 3, that is 5, 27, 28, 2, 8. Then we have 9, 2, 1, 295, 42, 0. We get 4,310 CW, joule per kilogram, right? Joule per kilogram per Kelvin, joule per kilogram per Kelvin. See, the theoretical answer we usually get is 4,200, but in experiments there can be errors, a little bit of errors here and there. So altogether, there might be some heat loss to the environment as well. So with all those errors inclusive, we get an answer 4,300. 4,200 theoretical answer, 4,300, it's very close. So it's not about what final answer we are actually getting, it's more about the procedure, the steps that we followed and why we followed each step, why we took each measure. Understanding that is most important for your exams. Clear? Right. Now what we will do, let's take some past paper questions from past exams to see how this has been tested. What kind of questions have come in the exam, we are going to see now. Alright students, now let's see some past paper questions from this area of experiment. Look at this is a very old one, 1981 new syllabus past paper. It says, not all the electric energy consumed by a bulb is transformed into light. We know, say if a bulb consumes certain amount of energy, not all of that is going to be converted into light. There will be some efficiency which is not up to 100%. If it consumes 100 joules of electric energy, not all 100 joules is going to be released as light. A portion of the energy consumed will be released as heat, right? The diagram shows the experimental arrangement to find the heat loss from the 12 volt, 21 watts headlamp of a motor vehicle. So basically it's a bulb with these specifications, 12 volt and 21 watts. You can see the arrangement here. seems like something like a calorimeter, water, stirrer. So same thing we did. We didn't use a bulb, we used a heating coil. Instead of heating coil, they are using a bulb here. No big difference thereafter. The temperature of 0.150 kilogram water in the polystyrene container increased from 27.2 degrees to 30 degrees when the circuit was switched on for 4 minutes. If the specific heat capacity of water is 4200, find the rate at which heat is released by the bulb. Right, the rate they are asking. So you have to divide by the time. Let's say the answer has to be MC delta theta over time. M 0.150 kilogram. C 4200. Delta theta from 27.2 it has gone to 30, 2.8 degrees. The time it has taken for that is 4 minutes. 4 into 60. Right? 60, 4200 is 70. Correct? Then 4, it will be 0.7. So this is 49 into 0.150. 49 into 0.150. 5 45 4 5 4 20 24 49 735 0.735 watts. Is it? Let's check again. Polystyrene, yes, 0.150 kilogram is correct. 27.2 to 30 is 2.8 degrees correct. 4 minutes means 4 into 60 is correct. So what happens? 0.067. Okay. Then 4 and 2.8, 0.7. 0.7 into 70 is 49. 49 into 0.15 must be 7.35. Must be 7.35. Right, 49 into 0.1 is 4.9, so it's 7.35 watts. So this is the rate at which the heat is being released to the water. Right, so our assumption here, all the heat released by the bulb has been gained by the water only. It doesn't get lost to the environment. There is no heat loss to the environment. The container doesn't consume any heat, right? Only the water. That's why we assume the water's heat gaining rate is the same as the heat emitting rate of the bulb. Next. What assumption has been taken in the above calculation regarding the polystyrene container and the surrounding? Yeah, so you can say no heat loss to the environment and polystyrene container. So basically, all the heat released by the bulb was gained by only the water. The container, since it is polystyrene, it's a rare conductor, so it doesn't consume any heat, is what we assumed. Next, what measure do you suggest to minimize the error due to the heat loss to the environment? We do this cooling correction, right? We start the experiment few degrees below the room temperature and end the experiment few degrees above the room temperature. Say cooling correction. Cooling correction. Start the experiment. start the experiment, few degrees, say approximately approximately 5 degrees below the room temperature, and end it few degrees above the room temperature. That's what we call cooling correction, right? So that the heat lost to the environment, heat gained from the environment, both can be assumed to be approximately equal. Find the efficiency of the bulb assuming no heat loss to the environment. So see, 21 watt is what it consumes. The electricity consumption per second is 21 joules. That's what we call 21 watts. And it loses 7.35. 21 minus 7.35 is what it converts as light. Yes. So that is 13.65 divided by 21 into 100. This we can divide, say if it is 65, because if it is 6 you get 126, and then another 105 is 5. 65% you are getting, 65%, or cancel 1 by 1, like divide by 7, you get 1, then 66 is 9, 35. Now you divide by 3, it's 65. 65% efficiency. This is what I told you at the beginning of this experiment. Out of the electric energy this bulb consumes, 35% is wasted as heat, and only 65% it gives as light. Next, if a calorimeter is used instead of polystyrene container in this experiment, what additional data will be required? So as I told you, since it is polystyrene container, it doesn't consume heat. So there is no heat loss to that. But if it is a calorimeter, then you must understand with water that calorimeter also consumes heat. So what other measure we need? We need the mass of calorimeter. Mass of calorimeter. Next, not only mass of calorimeter, you can say the specific heat capacity of calorimeter also. That's, they say data, right, not a measurement. Mass and specific heat capacity of calorimeter will be required. How do tungsten filament and fluorescent lamp produce light? Simple. Tungsten filament, what does it do? It gets heated. It gets heated. When it is heated, because of the heat, it glows. Right? It emits light. Whereas what happens in fluorescent lamp, there is nothing as heating happening there. There the electrons are going to be excited. Right? You give a high voltage difference and you excite the electrons, and they flow, or they go from one end to the other end, right, where they hit with or where they collide with some other particles, usually mercury particles, and when they hit with mercury particles, they emit light. So there is no heating process happening in fluorescence. That's the important point. You have to say, in tungsten filament, the filament is heated, and because of the heat, it emits light. Fluorescent lamp, the electrons are excited, and then because of that, electrons hit with mercury or with the gas inside the bulb, and that releases light. So we can say tungsten filament is heated and at high temperature it emits light. fluorescent lamp, what do you do? Electrons are excited using high voltage. Electrons will be excited and they flow from one end to the other end. They flow. When they flow, they are going to collide with the gas, which is usually the mercury gas. Yeah. They collide with gas in the bulb and emit light. Right. So, like, understand this is regarding a heat experiment. They are asking this question. So, don't go too much into detail. Simply, tungsten filament is getting heated, and because of the heat only it emits light. Fluorescent lamp doesn't have the process of heating. That's what you have to highlight here. Right. Not all the electricity and electrons related knowledge that you have to show here. Heating, no heating. Highlight that. Explain how the fluorescent lamp produces light with high efficiency. Same thing I told you now. In a filament light, since it is emitting light because of the heat only, there is a lot of heat loss. But fluorescent lamp, there is no heating process. Therefore, the heat loss is less. Since there is no heating process, in fluorescent lamp, the heat loss is less. Therefore, high efficiency. Therefore, high efficiency. Clear? Next. Look at this one. This is 1992 past paper, right? Very old ones, 1981, 1992. Same thing. But here what they do, what we had static water. We just took a container, we had water in it and we were heating it. Here what they are going to do, they are going to take water or any liquid that flows through this tube. So it's not static, it flows. It's the constant flow of or stable flow of liquid. See, diagram shows the experimental arrangement to determine the specific heat capacity of liquids. Constant flow of liquid is maintained in the glass tube AB from X to Y. From X to Y. The liquid is heated by heating coil within the tube. T1 and T2 are two thermometers to measure the temperature of liquid flowing in and flowing out. Okay, you have a T1 thermometer here, T2 thermometer here. Right. State the reason for using thin wire coil to produce heat. Why do we use thin wire coil to produce heat? You know, the heat produced will be equal to IV. IV means V equals IR, so that will be I squared R. I squared R. R, what is R? Rho L over A. Rho is the resistivity, L is the length of it, A is the cross-sectional area. Now understand, when cross-sectional area becomes smaller and smaller, R increases. When A drops, R increases. That explains why we have to use a thin wire. If it is a thin wire, it has a very low cross-sectional area so that the resistance is high. When the resistance is high, more heat will be generated, more heat will be produced. Right. So we can say when cross-sectional area reduces, the resistance increases. Resistance increases. and the heat generation rate will increase. Right? At short time, it gives more heat. Next, the heating coil is connected by a thick strip with the external parts of the arrangement. Explain the reason for using a thick strip. Let's have a look at the diagram again. See, the coil finishes here and then you are using a thick strip. The reason is this. Can you see part of this thick strip is exposed to the external environment as well, right? So what we want to do, we want to minimize the loss to the external environment, heat loss to the external environment. If we have taken the thin wire up to here, then in this part, whatever the heat by that wire coil, that will not be given to the water, that will be given to the environment, right? Because at this point you have anyway measured the temperature. Understand? So, we are using a thick strip because cross-sectional area will be bigger, A is bigger, so R will be lower, resistance will be lower, therefore the heat generated in these parts will be lower. We minimize it such that any heat loss to the environment is minimized. Okay. We will write that with high cross-sectional area, the resistance will be low. Heat produced by this strip and loss to the environment. Every time when you say heat loss, you have to say to the environment. Now, heat loss to whom? Heat loss to the environment is what we don't want to happen. Heat loss from the wire or the coil to the water is fine. So, if you simply say heat loss, then we don't know which heat loss you are talking about. So, you have to clearly say heat loss to the environment has to be minimized. Therefore, the heat produced by the strip and loss to the environment will be minimized. Next, what is the benefit of vacuum layer? Around this glass tube, if you have a vacuum layer, what's the advantage of that? You can reduce the heat loss to the environment by means of conduction. Heat loss, because conduction happens through a medium. If there is no medium, no conduction will happen. Vacuum, having a proper vacuum layer ensures conduction is minimized. Heat loss to the environment by conduction can be prevented. A particular apparatus is required to maintain the steady flow of liquid through the tube. Draw a labeled diagram of it and show how it will be connected to the tube. A steady flow of liquid. That means the flow of liquid, say it at the first second you measure the mass of liquid that came through the tube. After 10 seconds again you measure within 1 second how much of liquid has come. It must be same. At any moment you take 1 second how much of liquid flows through that, it must be same. Then only we can do this experiment, otherwise the calculations will be wrong. So how do we maintain that? I'll show you. There's a nice apparatus for this. I'll show you. See how it works is, look at this. I'll show you how it works. Right. We have a water bath like this. So how it works is, this will be connected to the tab, right? You have the tab. Right, this is connected to the tab. From the tab, water is going to come in. And this end will be connected to the exit. This is what is going to be connected here. Right. There will be a tab to close it and open it. So initially we close it and we open this tab. So once you open the tap, what will happen? See, the water will flow through here. The water will flow through here. It reaches here and it will get filled. Because this is also closed, so water gets filled. It will get filled until this point. The moment it reaches this point, then this tap is always open. This tube is always open. Then the water will start falling from here. It will start falling from there. So if you keep it open, the water level will always be maintained at this level. At this level. Whatever the excess water that comes in will exit from here. So once the water level stabilizes there, then you open this tube. Right? So one thing you must understand, the inflow rate must be greater than the outflow rate. Let's say inflow rate is alpha, outflow rate is beta. Alpha should be greater than beta. The rate at which water comes in, let's say within 1 second, let's say 2 liters come in. Then the outflow rate should not be more than 2 liters. It should be less than 2 liters. Let's say 1.5 liter. Then what will happen? 1.5 liter goes this way, 0.5 liter drops this way. So that the water level remains constant. If the water level remains constant, only the flow will be constant because the pressure is going to be same. Pressure will be determined by the height of water. So the height has to be maintained at the same level. So you bring in water, flow in. Inflow must be at a higher rate. And the outflow that you take to this tube must be at a lower rate. If you do it other way, let's say 2 liter comes in, you take 3 liter, then the water level is going to come down, isn't it? So make sure water flow rate is lower than the inflow rate so that the level of water, the maximum height of the water remains constant. It will never go beyond this because whatever the excess water will flow out from here. It will never be below this if you can maintain this outflow rate lower than the inflow rate. Understand? This is what we call the apparatus to maintain a steady flow of liquid. You have to have sufficient amount of liquid. That's why we usually do it with water. Right? Water will be abundantly available, so we can do it. If it is a rarely available material, then this method won't work. Huh? Right. Let's name it water tub. Let's say this is inflow. Outflow. Right, this is like the overflow. Overflow. Clear? That is the named apparatus to maintain steady flow of liquid. Clear? Next. A very high rate of liquid flow will reduce the accuracy of the experiment results. Explain why. If the water flows faster, then what will happen? See, within 1 second, the heat loss is going to be same. The heat given by the coil is going to be same. It is going to be I into V. That's all, I into V. And that is going to be gained by the water that goes through that or goes in contact with that coil within 1 second. So if the flow rate is higher, if you are sending water faster, within 1 second, a lot of water is going to go. So if a lot of water goes in, look at this. I into V is going to be mc delta theta. This is constant. Now m is going to increase. Why? You are sending it faster. When m is increasing, c is also constant. What will happen? Delta theta has to drop. That means increase in temperature will be very low. So what? Percentage error will increase. Imagine in the temperature measurement, error is 0.5 degrees. Okay. Suppose if delta theta is 10 degrees, which is good, 10 degrees. So out of 10 degree, 0.5 degree error means 5% error. 5% error. Suppose the temperature increment is only 2 degrees, then of that 2 degree, having a 0.5 degree error means that's 25% error. Suppose if the delta theta is only 1 degree, then 0.5 degree error means 1.5, 50% error. Do you understand? So when delta theta becomes smaller and smaller, the percentage error from readings will increase. Reading error percentage will increase. Right? So let's say that this will result in lower, or let's say this way, this will result in smaller increment of temperature. The percentage error of reading will increase. There is a percentage error, error percentage. Next. In addition to the readings of voltmeter, ammeter, inflow temperature, outflow temperature, what is the other important measurement required in this experiment? Right. See, now what we are going to calculate is this, right? IV equals mc delta theta over time. The IVT equals mc delta theta. So within 1 second, if you do, it's mc delta theta. I ammeter, V voltmeter, delta theta is there, theta 1, theta 2. C is what we are going to find. This is missing. This is missing. M over T. That means the rate at which water flows. In other words, how much of water, the mass of water that flows within a second or within a unit of time, that is required. So let's write it here. What is the other important measurement? The rate, or we'll say the mass of water, that flows in a minute, in a second. You can say in a second, or you can say in a unit of time. It can be minute as well, that's fine, because measuring within a second can be very low amount of water. So you measure it for a minute or 10 seconds, whatever. What we end of the day want is M over T, the rate. Name the apparatus required to get the readings in one above. You need a weighing scale, right? Let's say a chemical balance. You can say a chemical balance, or you can say 3-beam balance, or you can say 3-beam balance, 3-beam balance, 4-beam balance, right? Don't just say weighing scale, you won't get the marks. You have to particularly say this one. Next, at what instance will this measurement be taken? See, the moment you start the experiment, the temperature readings will not be stable. It will be increasing, right? You have to wait until the thermometers show you a stable reading. then we know everything is stable, flow is stable, the temperature increment is stable, then you get the reading. Before it becomes stable, if you take the reading, that is a wrong reading you are taking. Right, so let's say room temperature is 30. Let's say theta 1 is 30, then theta 1 has to be 30 anyway, initial temperature. Then the second temperature, let's say it's 40. So when you start the experiment, both thermometers are going to show you 30, and it takes few seconds or few minutes even for that second thermometer to go to 40. Right, the mercury column has to go up, right? So you have to wait until it goes up, stabilizes, wait for few more seconds and see whether everything is stable, then get the reading. So at what instance this measurement is taken? When the thermometers show stable readings. Stable readings. Next. Assuming no heat loss to the environment, write down an expression in terms of the measurements D1 for the heat gained by the liquid, IV equals alpha, they said alpha, M by T is alpha, right? Alpha C theta 2 minus theta 1. Usually we write IV T equals MC delta theta. Here there is no stopwatch or anything mentioned, so we'll take the rate, 1 second, fine. IV equals alpha C theta 2 minus theta 1. Here alpha is already defined, but C is not defined. Specific heat capacity of water. Specific heat capacity of water. Right? Quite simple, straightforward questions, isn't it? Let's see one more past paper, one more quite recent one, 2004 it has been tested. They have given you a 230 volt wall socket, beaker, insulating layer, bulb with holder. Figure shows some of the apparatus provided to you to experimentally determine the electric power dissipated as heat from 230 volt 25 watts filament bulb. You are asked to use water to collect heat given out by the bulb. Right. Now what do they say? Complete the above diagram by including the other required apparatus to show the experimental setup that you would use to perform this experiment, and label the items. Alright. So this time right, the wire has to be connected here, right? You don't need a separate switch because the wall socket will have a switch. The water has to be filled. Make sure the water level covers the bulb fully, right? Just sufficient to cover the bulb, you have to give it. Right. Water level is like that. Yes. And then we need a stirrer. Stirrer is missing here. Stirrer. We need a thermometer. We need a thermometer. Let's name them one by one. Stirrer. Thermometer. Water. Wire. Right? What else do we need? That's all. They have already marked bulb, beaker, insulating layers. They have marked. Next. Mark on the diagram the level up to which you fill the water. I already marked it here. See? So what you have to be careful there. Mark it sufficient to cover the bulb fully. Otherwise, the heat dissipated by this bulb might go to the environment. then our assumption that all the heat dissipated by the bulb is taken by the water, that assumption will be wrong. So make sure it's fully covered with water. Next, give two reasons to why it is advantageous to use a small beaker in this experiment. One, the heat increment in water will be significant. Why? You are going to use a little amount of water. So the heat increment, the temperature increment, right? Not the heat increment, temperature increment. It's heat increment as well, but what we read is temperature. Temperature increment in water will be significant. So what I told you in the previous question also, then when you measure it, the percentage error will be less, reducing the percentage error in readings. That's one reason. Second one, we can finish the experiment faster. How? Because there is only a little amount of water. Suppose you are waiting for 10-degree increment, that happens faster. So when that happens faster, the heat loss to the environment will be less, right? Because you are finishing it faster. When you do it for a longer time, heat transfer to the environment is bigger. So we can say experiment can be completed faster so that heat loss to the environment is minimized. There is another one, when it is a small beaker, the surface area is going to be less. When surface area is less, that also reduces the heat loss, because you know the heat loss from one surface to another depends on the surface area and the temperature difference. So when you reduce the surface area, heat loss also will be reduced. Surface area of beaker will be low. Reduces the heat loss to the environment. Heat loss to the environment, right? So there are several reasons why we have to use a small beaker in this experiment, not a big one. Give a list of apparatus needed to take measurements in this experiment. What are the apparatus? You need to measure the temperature, so thermometer. You need to measure the mass, so let's say 3-beam balance or chemical balance. Then you need to measure the time as well, stopwatch. Clear? Next. When this experiment was performed with 230 volt 25 watt filament bulb, the temperature of water was found to increase from 28 to 37 degree in 10 minutes. Mass of the water used was 240 grams. Estimate the electrical power that was transferred to water heat. Specific heat capacity of water is 4200. All right, okay. So it has to be M, C. They are asking estimate the electrical power, not energy. MC delta theta over T. M is 240 grams, 10 to the power minus 3. C is 4200. Delta theta is 9. 28 to 37 means 9. 10 minutes. 10 into 60. Now, these zeros can be cancelled. This is 7. So that is 0, 28. There is 9 as well. I missed the 9. So that will be 9763 240. 0 12 7, then 0 4 4 1, 0 2 1 5. With this 10 to the power minus 3, it will be 15.12 watts. 15.12 watts, right? So that's the rate at which heat is being dissipated into the water. The value obtained in A above may not be exactly equal to the power dissipated as heat from bulb. Give two possible modes of heat loss which are not taken into account in this experiment. Okay, heat loss to the environment you have considered. What are the other heat loss that can happen here? See, you assumed all the heat dissipated by the bulb is gained by the water only. The beaker is there. Even though it is insulator material, as a rare conductor, still it can consume some heat. It can absorb some heat. And then the bulb is going to have a glass. That glass can take some heat. Why? That was also initially at the room temperature. It's at a different temperature now. The thermometer is going to take some heat. Who cares about that? Thermometer also, like when the mercury expands only, it shows the readings. So thermometer, mercury and the glass around that absorbs some heat. So all these heat losses are not considered. So we'll write the beaker absorbs heat. The holder and glass of bulb absorbs heat. Thermometer absorbs heat. Stirrer absorbs heat. All the experiments we take stirrer, but here we have not taken it. Stirrer absorbs heat. Right, so there are several ways that the heat dissipated by the bulb might have gone to different places that is not water. Next. Certain manufacturers indicate a maximum power rating for electric lamp shades. Do you know lamp shades? See, when the bulb is this, if this is the bulb, right, we put a lamp shade like this. You put a shade like this so that all the light, all the light releases from here. This is the bulb, okay. It comes down so that you get more brighter light here. Otherwise, the light goes everywhere dispersed, right? Now it is going to be all focused downwards. So that's why you use a lampshade. They're asking you, on this lampshade, they mention the maximum power. Maximum power rating, they would say this is for 75 watts. Why do they mention that? You must understand, when this bulb is becoming with higher and higher power, the heat that is going to be released from this bulb is also at a higher power. You remember we did a question where we found, okay, 65% is going as light and 35% is going as heat. So imagine if the bulb is of 100 watts, if 35% goes as heat, every second 35 joule is going as heat. 35 watt is the heat generation. Suppose if this bulb is 200 watts bulb, if the watt is 200, then 35% of that, 70. So, depending on the power of the bulb, the rate at which heat is generated is also different. Imagine, at some heat generation rate, the materials of this lampshade can get burnt. That is also some material, right? It can get burnt, or the properties of that material can change. It can change its color, it can become darker, it might look burnt. So there is a limit. What is the maximum temperature? What is the maximum heat absorption rate of this lampshade? which the manufacturer knows. That is why they mention, okay, if they say 75 watts, you fix any bulb within 75 watts so that the lampshade will be unaffected, it will be intact. If you use a bulb with a higher power, lampshade might get burnt, it might sometimes even change its shape because of the heat, it might get bent. So we will say what shall we say? The lampshade may get burnt or turn into different color. What I mean by different color is not fancy colors getting burnt, like it becomes dark, right? So once it is becoming dark, then the light reflection would not happen. The purpose of lampshade will be lost. It will start absorbing the light. If it is a black surface, it will start absorbing. As long as it's a shiny surface only, it's going to reflect the light. So the lampshade may get burnt or turn into different color, that is basically burnt, when it is exposed to high heat. To avoid this, manufacturers mention the maximum power. So these are general knowledge, guys. This is general, like, okay, you know heat, you have studied this, but this part is a general idea you have to have. This, you won't find the answer for this question in the books. So every paper will have a couple of questions like this, testing your general knowledge. Whether you only know the book stuff, book knowledge, or whether you have the capacity to think in general life as well. Right. So this is one such question. Clear? Right. So this is the simple experiment where electrical energy getting converted into heat, and using that how we find the specific heat capacity of water. So there are different methods of this experiment. What we did in stable water, static water, we were using a coil and we were heating it. Instead of coil, we can use a bulb and find the consumption rate, the input power and the heat generation, the difference you can find, okay, what's the efficiency of this bulb? We can do that. Similarly, for a liquid that is flowing, how we do this experiment we saw in a question where you use a tube. Inside the tube you use the coil and you send the water or liquid at a constant rate and you measure the temperature difference and you can find C. Right? Likewise, different questions we have shown here. Right? Sometimes in this question you might have had a doubt, why didn't we use a voltmeter, ammeter? Because the two questions we did, we didn't have voltmeter and ammeter. But the middle one, second one I did, there was a voltmeter, ammeter. Because these are bulbs where they have rated it. They have mentioned this is the volt. This is the power of this bulb. So we know, like when you are connecting it to the main supply, we know it's 230 volt. And they say it's this many watts. So since the ratings are known, you don't need a separate voltmeter, right? But when we do the experiment with a coil, the coil's power might not be known. And like when we are using a battery or when we are using a voltage, a direct current supplier, we might not be sure about how much voltage it supplies, right? So there we use a voltmeter and ammeter to find the readings, right? So that's the end of this experiment. Practice all these questions and answers. Try to understand each step and measure that we have taken here. After practicing all this, let's meet up with another experiment.